pseudocode of repeated squaring. Yeah, yeah. Very simple. Here we can use the recursion. Yeah. We can use recursion to implement this method. Yeah. So we write this repeated squaring 2 parameters, x parameter and the degree n parameter. 2. All right. First, we look at the simple base cases. Yeah. We have 2 base cases. First one, n equals 0. Yeah. X to the 0, that's 1. So our function returns value 1. Yeah. First base case. Second base case, n equals 1. Yeah. So x to the first, yeah, return x. Yeah. After that, we do recursion. Yeah. All right. Else. Else, so we create an intermediate variable product. Store the intermediate result. This intermediate result we call the function by recursion, repeated squaring of x, second parameter n, integer division, n over 2, integer division by 2. Yeah. So it's another integer. Yeah. So we truncate the fractional part. Yeah. N over 2. Yeah. So we one recursive call here. Yeah. All right. So this product temporary variable, yeah, we will use later. Yeah. All right. Then we calculate the product equals result. Yeah. Result equals product times itself, square. Okay, all right. Then you will see when n is an even integer, when n is even, yeah, then no truncation, right? Yeah. If n is even, no truncation, that means this result is a good one. We can return it. Yeah. N is even. But when it's odd, there is a truncation. If there is a truncation, we need to make it up. Yeah, because there is a 1 extra x, we need to multiply it in our final result. Yeah. So let's check it. Yeah. X mod 2, if equals 1, odd integer, then we need to multiply our result by an extra x. Yeah, because we truncate it. Yeah. When we do this recursive call, we truncate it. Yeah. So now we add it back. Okay? Yeah. All right. If it's even, we do nothing. Yeah. Even, this, this number already a good one. Yeah. Then, at the end, we return the final result. Yeah. So it's a simple implementation, repeated squaring. Yeah. All right. Yeah. So. Yeah. Our module 3, in our module 3, we will learn recursion. Yeah. But it's okay. In our module 1, you can apply recursion if you like. Yeah. Next topic, B.6, repeated cubing technique. This time, we replace the square operation by cube operation. Yeah. Why we do that? Because it's a different method. Same idea, similar idea, but the method is slightly different. Yeah. Because we want to understand this question better. Okay? Yeah. All right. Yeah. Because when we have the background of repeated squaring, then we do this repeated cubing part by analogy. Yeah. We have experience. So we use our old experience. Yeah. So by analogy, we can understand this repeated cubing method. All right. Yeah, why structure of power of 2 is so special? Yeah, because sometimes we can consider power of 3 structure, right? Yeah, we know power of 2, one commonly used structure. Yeah, but here, power of 3 is a totally different structure, right? Yeah, so this time we use power of 3 structure as our building blocks for the intermediate results. Intermediate. This time we use power 3 structure. building blocks. Yeah. All right. Yeah. Yeah. So let me still use the same example we used in the B.5 previous topic. Yeah. All right. But this time I use power of 3 numbers to do decomposition. Yeah. All right. Yeah. We just, using the similar way. Yeah. What is the largest power of 3 under this n number? Yeah. 3 to the 4th, 81. Because 3 to the 5th, you multiply another 3, you will get 243 greater than this 217. So you cannot go one more step. Okay? Yeah. All right. So then, preparation. You need to prepare a resource pool, right? Resource pool. So here the question, how many multiplications do you need to prepare your resource pool containing the intermediate results? Yeah. All right. So the fastest way to get x to the 81st. Yeah. 8 multiplications. 8 multiplications. Yeah. Why we use 8 multiplications? Yeah. Let me show you step by step why 8 multiplications. Yeah. All right. First round, you take cube operation. This is cube operation, right? X times X times X. 2 multiplications, you get X cubed. Okay? Yeah. 2 multiplications. Second round, yeah. Now you have X cubed. You do another cube, X cubed times X cubed times X cubed. So another round, you need 2 more multiplications, you get X to the 9th. Yeah. Third round, 2 more multiplications, you get X to the 27th. Yeah. Fourth round, last round, another 2 multiplications, cube, you get X to the 81st. Now you add up these 4 numbers, 2, 2, 2, 2, 4 times, you get 8. Yeah. So in your preparation step, you need 8 multiplications to get these resource numbers. Okay, all right. Then, second round, we do decomposition. Power of 3 based decomposition. Yeah. All right. Yeah. All right. 217 equals 81. When you use 81, the largest power of 3, you can double it. Because even when you double it, still it is less than 217, right? Yeah. If you only use 181, then the gap is too big. Okay? Yeah. You need to use the power of 3 numbers to, fill the gap. Okay? To reduce the gap. Okay? Yeah. So here you use twice 81 to reduce the gap. Yeah. The gap number 55. Okay? Now you decompose this 55 number using power of 3, but you can still use 27 twice to reduce the gap number. Okay? Yeah, twice. Yeah. If you have more room, so you can use. Yeah. All right. Then the gap is 1. That's very small. So you can stop your decomposition. Yeah. Then you represent x to the 217th. Yeah. This time, because you use that 81 twice, so here you use x to the 81st, x to the 81st, you use twice. In your operand, twice. Okay? All right. X to the 77, you also use twice, because here you use coefficient 2, so you use twice. Okay, all right. Then, all right. So how many dots here? 1, 2, 3, 4. Yeah. So you need 4 more multiplications in your second round. 4 more. The first round, you need 8 multiplications. Second round, you need 4 multiplications. So total multiplication you need in this way, 8 plus 4, 12. Yeah. Do you still remember how many multiplications do we need in our repeated squaring? The previous method, repeated squaring, how many? 11. Now you can see in this particular example, repeated squaring does better than repeated cubing. In this particular example. Yeah. Here I do not say all examples, only this example. Okay? Yeah. Here, let me give you a different example. Let you see. Yeah. So which one performs better? Yeah. This one, repeated squaring performs better. Yeah. All right. Next, I want to show you x to the 15. 15. Yeah, small number. Okay? All right. Then, by our repeated squaring, okay? Repeated squaring method. Yeah. Preparation step. Yeah. X squared, x to the 4th, and x to the 8th, right? So this step we need 3 multiplications. All right. After this step, second round, yeah, x to the 15th equals to the 8th times x to the 4th times x squared times x, right? Yeah. So the second round, we need 3 more multiplications, right? So combine these 2 steps, we need 6 multiplications. Repeated squaring, 6 multiplications. All right. Now let's try our second method, repeated cubing method. Okay. All right. Yeah. Repeated cubing. Yeah. All right. Repeated cubing. Yeah. Preparation. X cubed. Yeah. So here, yeah, actually, yeah, if you do this way, so yeah, because you may do something unnecessary. Yes. So this way, because you may do something unnecessary. Yeah. So here, yeah. Here, let's do, you know, so we can change a little bit. Yeah. So how do we change? X to the 15. Can we write x to the 15 as x to the 5th times x to the 5th times x to the 5th? Cube operation. Okay? Yeah. There, x to the 5th. Can we write x times x to the 4th? So, yeah. All right? Yeah. X to the 4th equals x squared times x squared. X squared equals x times x. Now let's count. Okay? Yeah. 1, right? 1, 3. Okay? After that, 2 more, right? Yeah. Look at the total number of multiplications this way. 2 plus 3 equals 5. See? Yeah, 6 here, but this way we can use 5 multiplications. See? Yeah. Better, right? Yeah. Better. Better, but here you can see the reason we can do better here, we use cube operation, but also we use square operation, right? Yeah. So this here we use mixed operation. We mix cube and the square operations. Sometimes we use cube operation, sometimes we use square operations. We can mix. We can mix them. Okay? Yeah. All right, but the question, here, how do you, so here the question is, how do you find the best way, right? Because there are so many different ways. Think about it. Given an n number, you have many different ways to calculate, right? Yeah. Because even if you apply the mixed way, still you have many different ways, right? The question is how to find the minimum number of multiplications to calculate one monomial. Is it possible to design some algorithm you can find the minimum number of multiplications to calculate one monomial? That question you can think about. Okay? Yeah. That question not very easy to answer. Yeah. It is a little challenging. Yeah. In your homework assignment 1, so I give you one special monomial. I ask you to use the minimum number of multiplications to calculate it. Yeah. So one such question in your homework assignment number 1. Yeah. This week you will have quiz number 2. This week, quiz 2. Okay. Still Friday. Yeah. Homework assignment number 1. You will get that assignment next week after our Monday's class. After our Monday's class, I can assign you homework assignment number 1. Yeah. 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 All right. Yeah. So let's go to yeah. Yeah. So so here, I ask you, the general case. Yeah. For the pseudocode, we can do the similar way as the repeated squaring. Yeah. So here I still, write the pseudocode. Repeated cubing, 2 parameters, x and n. First, the base case is x equals 0 returns 1. Yeah. X equals 1 returns x. N equals 2 returns x times x. Yeah. Yeah. Then, else, the general case, our prod intermediate variable we store, thus repeated cubing x this times division by 3. N over 3. Integer division. Yeah. Integer division. If n is multiple of 3, then our result. So we equals prod times prod times prod. So we can get the answer. Yeah. But for n is not multiple of 3, if n is not multiple of 3, then 2 cases. Yeah. N mod 3 equals 1. Remainder is 1. Then your result, you need to multiply 1 extra x to your previous result number. Yeah. Yeah, because that remainder, you need to add it back. Add the remainder part back to your one more multiplication. If remainder is 2, you need to multiply x twice. Yeah. To recover that remainder part. Yeah. Yeah. So then, at the end, you return the modified this result number. Yeah. Yeah. So that repeated cubing. Yeah. All right. But in the project, I do not ask you to implement this one. Yeah. Yeah. All right. Yeah. So then, the last topic of part B. Yeah, one more topic. Yeah. Yeah. Taking advantage of the structure of Pascal's triangle. Yeah. So here the question is, we consider a special polynomial. It's not a monomial. Okay. This time, still polynomial, but it's a special polynomial. All right. Yeah. Because for the special polynomial, we can take advantage of the special structure to reduce the number of multiplications. Yeah. So what structure? Yeah. So there is an interesting structure, so we call it Pascal's triangle. That structure. Yeah. Right? Here, let me show you the Pascal triangle. Yeah. Yeah. The numbers like this. Yeah. So Pascal's triangle. Okay. So what's that? Yeah. So this special triangle corresponds to a special formula. So we call it binomial formula. Binomial formula. So let's recall the binomial formula. So we calculate this x plus y parenthesis to the nth. Yeah. Yeah. So we expand this function. Yeah. So we call it binomial formula. Yeah. Also Newton's formula. Yeah. Also Newton's formula. Okay. All right. So the formula, we need to use the combinatorial numbers. Yeah. Combinatorial numbers. Yeah. Like this. Yeah. And the combinatorial numbers defined using factorial. Okay. M factorial over k factorial, then over that m minus k factorial. Yeah. So this formula you can find in your discrete math. Okay. Discrete math. It's a binomial formula. Okay. All right. Then now we select different n number, then we can generate this Pascal's triangle. Okay. When n equals 0, x plus y parenthesis to the 0, because that's 1, the whole thing to the 0. It's a 1, so that's the 1 here. Okay. All right. The second row corresponds to x plus y parenthesis to the first. Because the coefficient of x is 1, coefficient of y is 1, so you put it here 1, 1. Okay? All right. Then the next parenthesis x plus y square. Okay? Square. 1, 2, 1 coefficient. Okay? X squared coefficient 1, x, y coefficient 2, and so 1, 2, 1 coefficient. Okay? Yeah. All right. So next one, x plus y parenthesis to the third, 1, 3, 3, 1, and so on. Okay. The fourth, 1, 4, 6, 4, 1. Okay. All right. Fifth, this next line, sixth, and the seventh. Okay. All right. Here you can see when we start from one line, the next line we can start in this way. Okay. Yeah. So each number we take the sum of two shoulder numbers of the previous row. Okay, the two numbers on its shoulder. Okay, yeah, left side, right side, two numbers. Yeah. Sum of them, you get it. Yeah, all right. So each number you have that. Okay, but nothing. So yeah, here nothing. Yeah, yeah. So. Then, for all rows, you have structure like this. For all rows, structure like that. Okay? Yeah. If you see the polynomial with this special structure, then you can write it as parenthesis x plus y to the, some exponent. Yeah. Yeah. This special structure can help you save certain number of multiplications. Yeah. How? Let me use a simple example to show you how to take advantage of the special structure to get a fewer number of multiplications. All right. Here, let me use this special polynomial, special structure. Yeah. Think about, if we do not use its special structure, how many multiplications do you need? If we use the Horner's rule, how many multiplications do you need here? Horner's rule. Any idea? Apply Horner's rule. How many multiplications? 4. 4. Not 5. 4. Okay? Its degree is 5, but why? Because look at its leading coefficient. Leading coefficient is 1, so the last multiplication you can save. Okay? You don't need the last multiplication. Yeah? Because leading coefficient is 1. Yeah. So by Horner's rule, you need 4 multiplications. Okay? All right. Now, let me show you the way, this time we want to take advantage of Pascal's triangle. Yeah? look at the coefficient corresponds to this row, right? Yeah, corresponds to that row. It tells us we should use this structure. Yeah. 1 plus x parenthesis to the fifth, that structure. Okay, yeah, yeah, all right. So by the Pascal triangle, we can write this polynomial as x plus 1 parenthesis to the fifth. Okay? After we have this structure, then the first multiplication, yeah, x plus 1 times x plus 1, x plus 1 squared. First multiplication. Second multiplication, square times that square to the fourth. Okay, all right. Third multiplication, fourth times x plus 1, yeah, x to the fifth, third. So we need a 3 multiplication. We can find this. So we can do better than Horner's rule. So when you take advantage of Pascal's triangle, if you can do better. You can do better. Yeah. All right? Yeah. All right. So after this topic, yeah, so we finish part B. We finish part B. Yeah. But now I want to talk about last 2 questions of our quiz 1. Quiz 1. Last 2 questions. Q9 actually you need knowledge from 2 topics. One, repeated squaring. One, another is Pascal's triangle. Because you also need a Pascal's triangle. All right? Yeah. You need these 2 topics to answer. Q9. Yeah. Q10. Yeah. Okay? You have Q10. Q10, you only need a Pascal's. So you need a Pascal's triangle. Yeah, actually also, because you also need, yeah, other than Pascal triangle, you also need a repeated squaring. Okay. Okay, yeah. Use these 2 topics to answer the last 2 questions. Okay, yeah. All right, so we finish part B finally. Yeah. Then we move to C and D. Yeah, so here we move a little slow than expected. Yeah. All right. Yeah. But because we spend this much time in our so module 1, we have part C, part D. Yeah. Part C, part B not as big as part B. Part B is the biggest topic. Yeah. But our first homework assignment, a lot of materials in this part. A lot of materials in this part B. Yeah. Many questions related to part B. Yeah. All right. Yeah, so I try to do a little faster, yeah, slower than I expected. Yeah, but anyway, yeah, I think we will be fine. All right. Topic, row of data structures in algorithms. C.1, search unordered arrays. It's a simple problem. Yeah, we can solve easily. Yeah. Search our problem number 4, search an unordered array. Yeah. Given an unordered array, yeah, and a search key K. Yeah. The question, find an index I such that K equals A of I. Yeah, so it's a simple search problem. The problem type here, search type. Yeah. And the data structure, we use array. Yeah. So the reference, I give you the reference here. Okay, all right. Yeah. So this is a very simple question. Yeah. So, we want to understand the role of data structure. Although here the data structure very simple. Yeah. Yeah. All right. So through data structure, we can make our data well organized. Yeah. Although here, actually the data in this question not well organized because unordered array. Yeah. Yeah. Not quite well organized. Yeah. Later, yeah. So in our module 2, so we will do a step to organize our data first. Yeah. So we will do a step, make unordered array to ordered array. You need to do sorting. You need to sort it. Sort your array to make it ordered. After you make your data ordered, then we can call it well organized, right? Yeah. Yeah. Because in that way, we can find our data faster. Yeah. When we work on ordered array, we can find our data much faster than we work on unordered array. Unordered array, then you need to, look from the beginning to end, right? Yeah. So do comparison from beginning to end. Yeah. But when you work on the ordered array, you do not need to do comparison from beginning to end. You can do the binary search, right? Binary search. You only compare some of the special numbers. Yeah. All right. Yeah. Because when you work on the well-organized data, you can find the required data faster. So that's the point. Okay. So why people spend computing resource to organize the data? Yeah. Because you will get a benefit later. Yeah. All right. Yeah. So you get a better performance. Yeah. In this question, the basic operation is comparison. Yeah. So we will, apply this basic operation, comparison operation, to solve this problem. Yeah. All right. So let's look at the general process. Yeah. Very simple. Yeah. So we compare the given key K with the current element, A of I, the current element. Yeah. All right. At the beginning, we initialize this I value to 0. So compare K with the first element in the array. Yeah. Two cases. Yeah. Yeah. If K equals A of I, then we find it. So we return this index number I, then we stop. Yeah. So the function terminates after we find this I number, index number. The second case, K not equal to the current element, A of I, yeah, then we need to do more iterations. Yeah. All right. So the new iteration, we compare K with the next element in the array, A of I plus 1. Yeah. So we keep doing this until we reach the end. So you reach the last element in the array. If you cannot get it, then we need to return a number that does not correspond to any index, -1. Yeah. So if you compare the given key with all the elements in the array, but still you couldn't get any match, then you return this -1 number, because when you see negative number, it does not correspond to any valid index number. So you know, it's a miss case. Yeah. So the key cannot be found in the given array. Yeah. Yeah. So that's the algorithm. Yeah. So some people call sequential search, and other people call linear search. Yeah. The name of this simple algorithm. Yeah. All right. Then here we want to do analysis on its efficiency. Do efficiency analysis. Yeah. So let us count number of comparisons. Yeah. But when you count number of comparisons, there are many cases. Many cases. Yeah. All right. So let's consider all the possible cases. We need to cover all the possible cases. Yeah. So the first case, k equals the value of the first element. Yeah. So you need a one comparison. Yeah. Second case, k equals a of 1, so you need two comparisons, and so on. Okay? If k equals the last element number, you need n comparisons. But still, there is another case, no match. Now, after you compare k with all the elements in the array, you couldn't find a match. So that no match case, you still need n comparisons. Yeah. So that's all the possible cases. Yeah. All right. Next question we need to answer. Yeah. So one basic concept we need to learn. Next. Yeah. All right. So first, the best case. Yeah. Because for all these cases, the number of comparisons we need are different. Yeah. So when we do discussion, in all these cases, we want to see the first concept, the best case efficiency. The one here is the best case efficiency. Yeah. The second concept, worst case efficiency. Yeah. The last two cases, so they both give us worst case efficiency and comparisons. Worst case. Yeah. So second concept. Yeah. But another concept also important, that's the overall efficiency. Yeah. So many times when we want to look at one particular algorithm, the best measure we want to use is the overall efficiency. So not the best case efficiency, not the worst case efficiency. We want to use the overall efficiency. Yeah. So that is the average case efficiency. If you want to describe the overall efficiency, the best number to use, average case efficiency. Yeah. So here we need to study a concept, the average case efficiency concept. Yeah. All right. But the question is, how do you calculate the average case efficiency? You need to do calculation. Yeah. You need to really do some important calculation. Yeah. So the question, yeah, how do you include all the cases when you calculate average case efficiency? You have to include all the cases. You cannot miss anyone. Yeah. But the question is, how do you include them? There are many different ways you can include all the cases. But which way is the best way? Here we need to consider that question. What is the best way to calculate average case efficiency? Yeah. All right. How to know all the cases? Here we already list all the cases. Yeah. So here that's not a question. Yeah. So in other questions we need to list all the possible cases. Yeah. Yeah. But the next question, how to combine all the cases? How to combine all the cases? Yeah. Yeah. All right? Yeah. All right. So here, how to combine? So here you can see all the numbers. Before we proceed, I want to ask you one question here. How to combine? regarding this question, how to combine all the cases. Here, let me ask you one question. Can we use this way to combine all the cases? Yeah. Let me add all these numbers and another and, yeah, because I add up all these comparison numbers for all the cases, then divided by total number of cases. Yeah. How many cases here? Total number of cases. N plus 1, right? Yeah. N plus 1. Yeah. Do you think this number gives a good average case efficiency number? Is it a good way to calculate average case efficiency number? Yeah, because I combine all the cases. I do not miss anyone, okay? And I try to use the fair way, right? Yeah, I add them up, then divide it by number of cases. Yeah, it's a fair way. Can you see any problem here? If we do it in this way, can you see any problem here? Something not quite right. Something not quite right here. Yeah, yeah. Yeah, there is a factor. So here we miss one important factor. If you calculate this way, most of the time it's not incorrect. Most of the time it's incorrect. The reason is, so here I'm talking about appropriate assumption. Yeah. One important information is missing. One piece of information is missing. So what information? Yeah. Because here, no match. What is the probability for the no match case? Do you know that? Because no match case, the probability could be large, could be small, right? Sometimes large, sometimes small. So that probability factor is important. Here, not given. If it's not given, we don't know. If we do not know that number, then you cannot find a fair way to calculate average case efficiency. Yeah. So for that reason, we need to make appropriate assumption. We need to assume that probability. Okay? Yeah. Yeah. All right. So let us look at the average case efficiency. Yeah. All right. Here, we need to make assumption. Yeah. So here, yeah. But here, for this part, if we do not consider no match case, consider these cases, then we can assume that each case, all the cases have the same probability. Yeah. 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 So that's reasonable assumption. Reasonable assumption. Yeah. But when you consider the probability for index case, yeah, whole index case, okay, and the probability for no match case, -1, because the function returns -1, okay, yeah, then you can use a variable p, yeah. So if it's not known, you need to use it as a variable. But in the real world application, you need to find that probability number first before you do the calculation. Yeah. Otherwise, you cannot find the average case efficiency. Yeah. All right. So the p number should be between, because it's a probability number, between 0 and 1. Yeah. Then, the no match case, its corresponding probability is 1 minus p. The complementary part, 1 minus p. If you know this little p, then you can write the correct version of average case efficiency. Correct version. Yeah. All right. But the question, before I do the correct version of the average case, yeah, I want to answer this question: how to get that little p? Right? Yeah. Yeah. So you need that number. Yeah. But how to get that p? Yeah. So in the real world situation, to get that p, you do statistics based on the history data. Yeah. The history data. Yeah. All right? So you run the linear search many times. Yeah. Yeah. So you have the history data. Okay? Yeah. All right. So you do statistics. Yeah. Yeah. So then you can estimate that P number from the history data. All right. Yeah. Or we can do dynamic statistics. Yeah. So you just, do it on the fly. Yeah. So every time when you have a input data, then you do statistics. So that's the dynamic data. So you do statistics data dynamically. Yeah. Yeah. Every time when you have a new input data, so you do one statistic calculation. Okay? Yeah. Yeah. Like that. Yeah. To estimate that P number. Yeah. All right. Now here we assume we have P. Okay? So we have that P. Yeah. So we want to do analysis to find the best formula for the average case efficiency. Yeah. All right. When we do it, yeah, so we treat all the cases as two subcases. Yeah. The first subcase, yeah, so all these, index case. Yeah. If the function returns a valid index number, we treat it as the first subcase. Yeah. The second subcase, that no match case. Yeah. But for the first subcase, can we calculate the average case efficiency only for the first subcase? Then we can use this formula. Yeah. Because we assume all the cases, they have equal opportunity. All these, sub yeah, so here the, sub cases, yeah, whatever, yeah. All these little cases, they have equal opportunities. Yeah. So we can add them up divided by n. Yeah. But that's the average case only for the first subcase. For the second subcase, yeah, second subcase, only there is one case there. So when we take the average on one number, so its average case number is the same number n. Same number n, okay, for the second subcase. Yeah. Now, after we calculate average case number for each subcase, then we combine these two subcases with appropriate weight numbers. Weight numbers. Yeah. Here, what we are doing here, we calculate the weighted average. So this P, we treat it as the weight number for the first subcase. Yeah. The weight number for the second subcase, 1 minus P. Then we do weighted average. Weighted average. So what's the weighted average here? Okay? All right. So here, this is a weighted average number. How to write a weighted average? The first average case number, yeah, so this number here, okay? The first average case number, multiply its corresponding weight. P is the weight, okay? The probability number, we treat it as the weight number. Then, plus the average case number for the second subcase, n. Then multiply its corresponding weight number. Yeah. The probability, its corresponding probability, we use it as the weight number. Yeah. So this is the weighted average. Yeah. So this weighted average gives us the best average case efficiency. Yeah. So later, when I ask you to calculate average case efficiency for one particular algorithm, you should use the weighted average. Okay? Yeah. Like this. Yeah. But that probability, in different questions, you use different ways. Yeah. Yeah. probability number. Yeah. Similar to this one. So this example, you can use as your reference. When you calculate the weighted average, use this example as your reference. Yeah. Similar to this example. Yeah. All right, yeah. Yeah. Okay, then, now, next concept. Next, yeah. I have 5-something minutes. Yeah, let me talk about one more concept. So then we finish this topic. Yeah, and we can stop today. The next time, in the first half, I want to complete. So the first half, yeah. Yeah, I try to complete the remaining part in the first half. Yeah. So then in the second half, I can start module 2. The second half next time. Yeah. All right. Now, then I want to use about 5 minutes to talk about a new concept. Here, what do we want to do here? So look at this, the whole formula here. Okay. Yeah. Yeah. So there are many terms here. Yeah. And what do we want to do here? We want to do something approximation. Yeah. Here we want to do approximation. Yeah. We know this formula is an accurate version. Yeah. Accurate version. So precise formula. Yeah. But in our computer science calculation, we like to use approximation a lot. So so many times we do not use accurate formula. We use approximate formula because approximate formula is simpler. Yeah. Yeah. And we don't need very accurate. Yeah. So we allow some small error. Yeah. So we can draw some minor terms. Yeah. We keep the major term. Yeah. Then that major term, that part, much simpler. No? So we use simpler formula to do calculations. Yeah. That's very common. Yeah. Here I want to show you that approximation way. Yeah. All right. So here you can see relatively complicated in many terms, right? Yeah. So here, let me do some combination first. Yeah. Here we know n is a variable here, n variable. And this p is a constant. P is not a variable. Okay? P should be given. So we treat p as constant. Constant. Yeah. So fixed, always fixed. Yeah. After we have that p, we always fix it. Yeah. And we can change the n number. But p always fixed. Yeah. All right. Then when we combine the terms here, yeah, let us write the term based on the variable n. Yeah. All right. So the n number is our main part. Yeah. N number, most important, this variable number. Okay? All right. So then n, what is the coefficient of n? What is the coefficient of n? Okay? All right. N, the coefficient from the first term contribution, 1/2 times p, right? Yeah, because this p, you need, so the contribution of the coefficient from the first term is 1/2 of p. Then the coefficient for n, contribution from the second term, 1 minus p. So 1 minus p you need to add to 1/2 p. So the coefficient, what do you get is 1 minus half p. Sorry, 1 minus, so this 1/2, you have a p here. So parenthesis, yeah. Parenthesis of 1 minus half p. That's the coefficient times n, after you combine coefficients. All right. Then the constant part, after that, the constant part. Yeah. All right. So 1/2 times p. So the constant part is 1/2 times p. Okay? All right. So this is accurate formula, right? So no approximation. But yeah, when we do approximation, we want to drop some minor terms to do approximation. Yeah. For example, this 1/2 p, this term very small, right? So we drop that 1/2 p term to make it simpler. Okay, make it simpler. So we only take the major term. Yeah. Parenthesis 1 minus half p times n. That's the major term. So that major term here we give a new concept. We call the dominant term. That major term, so that's so-called dominant term. Okay? Yeah. So what's the dominant term? Yeah. So we drop that minus term. So parenthesis 1 minus half p whole thing times n. That's the dominant term concept. Okay? Yeah. Because this concept we will use in our module 2. This is a basic concept we will use in our module 2. Okay? Yeah. All right. Dominant term. All right. So the dominant term gives a good approximation. So how do we do approximation? We just take the dominant term as the approximation of the original formula. Yeah. All right. Oh, yeah. Time is up. So my alarm clock. Okay. All right. Yeah. So not like last time. Yeah. So yeah, but also I finished this topic. Okay. Yeah. So dominant term. Yeah. So minor terms can be ignored without significant loss. Yeah. But this significant loss thing, I will explain this. What do you mean significant loss? I will explain this concept in module 2. Yeah. In module 2, I will, why when we cross out minor terms, we do not miss much. Yeah. So I will explain that phenomenon in our module 2. Yeah. All right. Yeah. So that's it. Yeah.